You want to rotate it, use Control R. Or you can use the rotate function out there. A lot of times it's simpler if you just do the key. So Control and then R, you can rotate it. And there you go. If you want to put it down, left, right, you know, put it down. And if you want another one, you move it somewhere here, let's say, and then Control R. And put that down.
Okay.
I'm sorry?
Okay.
Well, then you can scroll in and out like that. So this is not a big, so you don't increase the resistor size by doing this. But you can put values here. I mean, it should be obvious, but I don't know this value. C gets the capacitor from it, and Control R rotates it, and I can put that one here. If you want to move things around, you can use this, either one of these. Like this one will drag things up and down. Drag actually keeps the lines intact. You can sit over here. I'm sorry?
I just got here, so I'm fine.
You can sit. You want to sit here? You can sit down here if you like. This is a box seat, all right? Two seats. So, and you can move them around. I'll show you a little later how you do that. But then, if you want to zoom out, you can use this. Right? And I mean, if you want to have access to most components, the most used ones are here. You know, resistor, capacitor, inductor. You're going to need a ground in your circuit. And here's ground. I can click this and get a ground and put it in my circuit. Or I can type G, ground. You can put it right here, for example. Okay. You can turn on the grid, and if you want, for example. But the entire component library is right here. If you click that, you'll get most of the parts. Now, I didn't bring my ideal op-amp, but op-amps are here, but these are linear technology. I mean, these are actual op-amps. They're not ideal op-amps. But, you know, you can get all the components that I've shown you there. If you go there, like capacitor is right here, cap. And as you click it, you'll see different things showing up. And, you know, if you want a resistor, it's right here, RES. Voltage source is right here. I mean, everything is here. And you have to just kind of look around to see, like a current source, right? It's like, yeah.
Do you count like a library there, microcontrollers too?
No. That's too, well, normally for microcontrollers, you have to specify code, and this doesn't take care of that. If you want to do something like that, you'll have to go to a slightly different kind of language. Usually like Verilog or something like that. Or compile your, or use a code simulator. Have your microcontroller run in code and have your circuit run in Spice and your simulators talk to each other. That's tough. But this one doesn't have that option. However, you can solve, you can model discrete time circuits. Z domain, S domain, you can actually do it in here. Pure S domain, like MATLAB basically. Okay, so this is what we have so far. What else can we do? Well, we can put a voltage source. Okay. What I want to do is I want to get the transfer function of this thing, and the voltage source is right here. And this is generic voltage source. Okay. And then get another ground. Maybe put that right here. And maybe this is too small. So what I'm going to do is I'm going to increase this a little bit. Okay. Or I can just do zoom in. Just do the content. If you want to remove something, cut it. Okay. So then the wiring is kind of nice because it allows you to do like sort of quick wiring, as it's called. So I can click on this to do the wiring, connect the components, or I can F3. Same thing. And I can just do it like this. I can just go through the components actually. And it won't short them out. LTspice will short them out. Don't try this at home with LTspice. You'll get shorts. But I can just do this and then right click, they're connected. You see? And then F3 again if you want. This.
That F3?
F3, yes. And if you don't know, you can always go and look at the command here, and you can see right about there. Draw line, F3. Place ground, G. I mean, they're kind of there. After you look at this a few times. I'm sorry? Draw wire. It's over here.
Oh, draw wire.
Yeah, that's what I said, draw wire.
You said draw line.
Like the voltage source.
Look at the time. All right. You guys are so critical, and since you're so picky, I think I might be very picky on your quizzes too. Use a lowercase r. Do you have a question?
Yeah, she said that
There is no ideal op-amp in the. There is no ideal op-amp in LTspice itself. However, if you go to the LTspice page, you can download an ideal op-amp. Okay? In fact, it's in the libraries, and I don't know if we'll have enough time to show it, but I can show that too. You go to the web page and download, and I'll show you that. Okay. Remember, I gave you those steps to go and install, and there's an ideal op-amp actually right there. But right now, I just want to put the component values in and show you what happens. What you do is these R1s and C1s and R2s, you don't touch those, right? Those are the reference designators. The reason I'm telling you that is every term, there are people who want to change these values and get errors because you can't change. Those are not the values. The values are these. All we got to do is right click on this and enter a value. And if you look at the lower corner here, it will usually tell you kind of what to do, right? I'm doing this because it's kind of cutting it off. It says right click to edit R, the value of R1. So R is the value, R1 is the designator. You can also change the designator too, right? But you don't put a number there. Like I can call this R1A if I want to. It doesn't really matter. I'll go up here and put in component values. Okay, what should I put as component values? I'm going to choose what I had over here. I'm just going to use those exactly. I'll use 10 to the minus 2, 1 over 900. Okay. So this is 0.01. Okay. 1 farad. Okay. And then I'll use what? I'll use 1 over 900. You can actually put in fractions like that, but they need to be computed, so the directive to ask LTspice to compute something is to put in curly brackets. So if we do curly brackets 1 over 900, it'll actually compute that value. You can just leave it in a fraction like that. It's fine. And for AC analysis, you want an AC source. You don't want a sine wave source, actually. You want an AC source, right? Because we're doing phasor analysis here. So you go to advanced, and all you have to do is specify right here amplitude and phase. Amplitude 1, phase 0. We don't care about this because it's all linear. Plus, we're just going to do VR over V anyway. We don't care. Okay? So, you can go and label the terminals as well. If you don't do that, it'll just number itself. So, right now, if you look at the schematic, there's already a netlist associated with it, and if you go to View Spice Netlist, you'll see that netlist right here. R1A, etc., and the numbers are at the end, like 1 over 900 are the component values. So that's what I was saying. If you go to, let's say, R2 and change it to 300, your first number will be 300. It's not the reference designator. Spice looks at the first letter to tell us what kind of component it is. Things that begin with R are resistors, V are voltage sources, C are capacitors, etc., okay? Things with an asterisk are not read. The first line is a comment. It's not read in, actually. Okay, so you can see it live. And once you've done this, it's a good idea to go here and, label these nets. So you can put in, for example, here, and place it. And if you do that, these two will be shorted, actually. You can do that if you want to, but in this case, you can right-click and change it to Alt. And it's done. If you go to the netlist again, you'll see that it actually made the update. See? And 0 is ground, by the way. You have to have a ground in each circuit, like it or not. Spice doesn't like floating circuits usually. You have to have at least one node that's ground, and there has to be a DC path to it. Okay? That's common with any Spice that you'll use. We're ready to simulate, and all I got to do is hit the running guy. The only thing I haven't specified is what kind of analysis, and it'll actually ask me. So it's asking me what I want to do, and I really want to do EC analysis, and we're going to sweep the frequency variable, and you can sweep it any way you like. Normally we sweep in decades, number of points per decade. By the way, as I'm saying this, as I'm filling these out, we're entering in a line of spice code here. If you know how to enter the spice code, you don't have to do this. I normally don't do this, but I'm just kind of showing you where it's at. Number of points per decade, okay? I'm sorry? How did I get this? Oh, when I hit the simulate button, there was no simulation command. So it's asking me. So, decade, number of points per decade, maybe 100 points per decade, start frequency, in hertz by the way. Let's say 10, or let's say 1, 2, 10,000, I can put K if I want to, K is understood, 10 here, okay, and then it'll give me a line, and it actually just simulated it, that fast, so, and here's the line. So if I want to change this, if I want, I right-click on it, and I can just change it to anything that I want. Increase the frequency and things like that. Click, and you get a plot. And this is the phase and dotted, and the solid line is the negative response. And if I don't want the phase to be plotted, I bring the cursor here, pick up the ruler, left-click it, and I say, don't plot phase, go away. Other things I can do is, again, just move it too much light, and maybe it's getting washed out, but you can still see it. All right. You can see, you can put in, let's say, right-click on the graph face. You can put in the grid, for example, and you can see the grid. You can make the line thicker by going to waveforms and putting plot data and thick lines, for example. That's one other thing I do usually to show it on screen. And that's your frequency. And you can see it's not a solid line, right? It's the curved line. But if you had a solid line in mind, you can kind of guess at where it is. Now, notice the horizontal is not omega yet. There's a way to do that. I'm going to show it to you later on. Yes?
Can you actually plot asymptotic correlation?
Yes, you can do it, but it's a special custom library by me, and I will give it to you sometime. I don't want to overwhelm you now with too much stuff. But this, and by the way, you say, well, I don't see this flattening out, right? So you can truly go down to minus 20 dB, so 0 dB in this case. So what you might want to do is go back to the simulation here, okay, and say, I want to plot for even lower frequencies. I want to go to 0.01 hertz. Okay, hit OK, and run, the running guy here, and there it is, right? So this kind of looks like, I mean, forget about the frequency points, right? But it does have that shape. It's minus 20 dB here. There's a minus sign here, right? And a high frequency gain is 0 dB. We kind of knew that, right? Because the factor out front, remember on the passive one was like C1 over P1 for that RC circuit. And that is actually what we expect. The frequency points are in hertz, not in radians per second. But if you made the conversion, you would see that they're right on. Except that at the corner frequencies, we're off by 3 dB from the straight line approximation that we think. Yeah. You can't do it on this one because we didn't do DC now. But if you look at the surface that we have up there, you will see